So, we started with defining Gaussian mixture models, which are just superposition of k different Gaussians, and in a general mixture model, instead of a Gaussian you can use any other probability distribution. So, the three important set of parameters are the mixture weights, the mean and the covariance matrices of each of the Gaussians, and there are k components. I have still not come back to someone had asked how do we estimate k, we will see that today. We saw some examples of how to fit Gaussian mixture models. We saw that Gaussian mixture models are good models when there is naturally good models when there is a clustered structure in the data, so that each of those clusters can be nicely fitted with a Gaussian, and then we saw that the Gaussian mixture model can be very intuitively explained through the generative procedure, where you assume that there is a latent variable that basically tells you which Gaussian to pick, and then once you pick that, you sample your or you generate your data from that particular Gaussian. Right. I think this is very important to remember, as it makes a lot of the math, it makes sense of a lot of the math. Then we saw our posterior probabilities, which are also called responsibilities. The posterior probability of the latent variable taking a value k given the data, and we saw it coming up repeatedly in all our calculations. So, the estimation, assuming that we know k on p dimensional data, the estimation problem is to estimate these pi k's, mu k and sigma k for each of the Gaussians, right. And we saw that initially, we first saw that if we assume we know the responsibilities, then the math works out very nicely and we get very intuitive forms for the different parameters. Right. And then we designed an iterative algorithm that essentially guesses the parameter first and computes these responsibilities, and then refines the guess in each iteration. And later we saw that this actually is the EM algorithm for Gaussian mixture models. Right. So, let us see this more carefully. In general, EM had been proposed for data which had some hidden data points not known when you get the data set, so Z is we denote that hidden data by Z, and for the purpose of this discussion we assumed it is discrete, and later we saw that in the case of Gaussian mixture models we can take the latent variables to be hidden. That is a common trick used in many other models. And then we saw that EM is a good approach to take when the joint likelihood, the complete data likelihood can be easily parameterized, and if that is if we make that assumption, then we see that we can get the marginal likelihood also, right. So, what is EM? The key idea is that, so this is the key idea. We take the expectation of the log likelihood of the complete data under the distribution of the latent variables, assuming the guesses of the parameters that we have made, right. And instead of computing the maximum likelihood, we compute the parameters that maximizes this expectation, and this is the key idea of EM, right. Actually, if you remember this, yeah, I mean this should be the main takeaway of this class, this formula. So, then we saw that if we use this formulation, then for Gaussian mixture models we essentially get back the iterative algorithm that we had guessed, right. We use this, so this expectation is also called Q function in the literature. We get a very nice form for the Q function. The reason So, the reason we get a nice form is one, because we are using an expectation operator which pushes the summation to the outside, and the second reason is that we get the logarithm of this logarithm of the Gaussian without any summation inside. The expectation pushes it outside, right. That was the reason why the math worked out, and the derivatives became very easy to calculate for the case of Gaussian. Right. We essentially got back the same formulas for mu k, sigma k and pi k that we had guessed earlier, assuming that we know the responsibilities. Right. So, the general EM algorithm is this: guess the posterior distribution of the hidden data or the latent variables, and then refine your guess by maximizing the Q function, which is the expectation of the complete data likelihood under the distribution of Z with your current guess. And today we are going to see that this procedure is nice because it guarantees that the likelihood will increase in every iteration. So, whatever likelihood you start with, at every iteration the likelihood is going to increase. So, that is what we are going to show today. So, this is the complete EM algorithm for estimating the parameters of a Gaussian mixture, and we also saw that if we assume that the only parameter to be determined is mu k, which means we assume that all the Gaussians are spherical with known covariance matrices and pi k is set to 1 over k, then essentially what we get back is the k means algorithm. Right. So, we can see this. So, this is the theoretical guarantee I was talking about. EM monotonically increases the observed data likelihood, and until it reaches some local maximum. It can also get stuck in some saddle point, but it's so it does not give you the global maximum, it only gives you it only takes you to the local maximum. So, let me show you that simulation that I had shown you last time. So, I generate some data, okay. 3 Gaussians. This is what the data looks like. It was generated like this by taking those 3 means and covariance matrices. This is what the fitted density looks like. Right. If I run EM once, right. So, this time EM did not do well. You can see what happened. The means that it inferred where 2 of them are here and the third one is here. Because these 2 clusters are very close together, it assumed that it is being generated from the same Gaussian, right. Let us now run this. So, I ran this 10 times, and what I see is that the likelihood for each of this run, the likelihood keeps increasing, right. Every time for each iteration the likelihood increases. Sometimes it gets stuck and at a saddle point or a fixed point, and then does not increase, right. So, this is the typical behavior of EM. In fact, this is a very good debugging tool if you are writing EM algorithms for your models, and if you see that the likelihood is not increasing, there is some bug in your program, right. Now, let us see in these 10 runs, these are the likelihood values it got stuck at the end, or it stopped at the end, not necessarily stuck at. So, if we see the minimum of these, that is the second one, and we see the fitted density when we use that run, you see the fit is not very good. If we take the maximum likelihood among those 10 runs, it is the 9th one, the fit is much better now. You see, this time when the likelihood was in the 9th run, the likelihood was the highest among these 10 runs, and the fit was also much better, right. So now let us prove that what we saw there is true in all cases, that it actually monotonically increases the likelihood in every iteration. So the main result we will need to prove this is Jensen's inequality. Are you all familiar with this? No? Okay, it is very simple. So if you have a convex function, then and you have a linear combination of these points xi, then the convex function applied to the linear combination is less than or equal to the summation, the linear combination of the of fxi, where the function is applied to each of the xi's, right. And what we are interested in, you might have guessed, is the logarithm function, because log is what appears in our summation. And if we use the fact that minus log x is convex and put it here, then we get this inequality, right. It is the same thing. The function is just the logarithm. So what we see is that log of a summation is always greater than or equal to the summation of those lambda I times log xi, right. So let us start with so we have these latent variables or the hidden variables in some cases. Let us assume that let us assume that q is some arbitrary distribution over the latent variables. We will not define what q is right now. Okay. So because these are probability values, each of these q zns for each latent variable is greater than 0, and the sum over all zn is equal to 1, right. So now let us take the likelihood of our data, and we express it again as usual in terms of the joint likelihood with respect to the latent variables, and then we just multiply and divide by q of zn, right. And now because of this condition, q of zn is the same as lambda I is here, it follows the assumptions of Jensen's inequality, right. So we can apply Jensen's inequality here and get a lower bound on this expression, right. So basically take the summation outside and get the log inside, and this lower bound just follows from Jensen's inequality, right. All we have done is applied this inequality, and lambda i's are the q zns here, because their probabilities, the assumptions are true. Okay. So now this logarithm can be written as a difference of the log of the numerator minus log of the denominator, and what we get here, now this expression should start looking familiar to you. This is just an expectation, is expectation of the complete data likelihood under the distribution q, right. So this is something that we have been working with in EM, and on this side we have the entropy, right. So this entropy term is not going to play a big role here, but we are going to be interested in this. So let us call this q. This is although it will be the same q eventually, I have used a different q here, because right now we do not know that it is the same q. Okay. So what have we got? We have got a lower bound on the log likelihood, right, and we have proved this for any arbitrary distribution, right. We have not said that it is the distribution of the latent variables under the guesses of the parameters that we had. We did not say anything about that. So now the question is, which distribution q should we choose? Any guesses? So what we have is a lower bound. What kind of distribution would you like to choose? No guesses? Think iteratively. All right. So we want, since this is a lower bound, we want the bound to be as tight as possible. Okay. So we will choose a q such that we want to maximize, such that we maximize the lower bound to reach the actual likelihood. Right. That's a natural choice when you're dealing with bounds. Right. So let's see how we can choose such a q. Okay. To do that, let's just look at this expression again. We will ignore the summation n, because we'll bring it back later, but I've just not written it. So this is the original expression for the lower bound. Right. The q function is here. I've just written that again here, and now I'm just expressing this joint likelihood. I'm factorizing it in this way. Right. So you have the probability of xn zn. The joint probability is just the probability of Zn, and then the probability of Zn given theta. So there should be an xn Zn here. Right. Yeah, it's fine. No, it's fine. Yeah, it's fine. Right. So this is just a factorization of this probability, and then I just separate it out in a different way this time, and what we get here is a term which is just the Kullback-Leibler distance between QZN and this probability, this distribution. Right. It's the negative of the KL divergence between QZN and probability of Zn given xn and theta. Right. And this term is essentially summing over all Zn for this. So this is independent of Q, and we just get logarithm of we just get the likelihood back here. Right. And here we have the negative KL divergence between these two distributions. So if we want the lower bound to reach the actual likelihood, which we are getting here, we want this term to become 0. Right. And that we can do by just putting QZN equal to this probability of Zn given xn theta. Right. But again we come back to the same problem that we do not know the actual theta, the curly theta, but in an iteration of Em we have guessed the value of theta m. So we can use that value of theta m to and use that probability distribution as q. Okay. So what we get if we use this value for qm, which is the probability of Zn given xn and the guessed theta m values, is nothing but this expectation which we saw coming up here, except that instead of q we are using qm, which is based on the current guess value, and we are getting the entropy term, but this entropy term is independent of the thetas. So when we maximize this in our m step of Em, this does not play any role, and what we are eventually maximizing is this expectation of the likelihood under the distribution of Z. Right. So let me again summarize what I did. I took the log likelihood. This is the likelihood that we are interested in for getting maximum likelihood estimates. Using Jensen's inequality, I got a lower bound. The lower bound was in the form of an expectation, right, which is the expectation we maximize in the E step if we take Qm to be exactly this probability distribution. And this probability distribution turns out to be exactly the probability distribution to take, which will maximize the lower bound to reach the actual data log likelihood at that step. Right. So what have we done? We have maximized, we have taken our current guesses and chosen a value of Qm that will reach the actual likelihood with respect to the current guess. Right. But that has not brought us closer to the real theta, right? We are still working with our guesses of the parameters. Is that clear? So here comes the crucial part, right. So at the mth step we took QM, the distribution of Zn, to be exactly this probability distribution, the posterior distribution of Zn given the data points and the current guesses, and we saw that this likelihood is exactly equal to the KL divergence plus the log likelihood. And because this KL divergence becomes 0 at this point, this Q function is exactly equal to the log likelihood, which means the lower bound is tight after E step, which is what we wanted. And so maximizing Q after this is going to maximize the data log likelihood also. To see that, see this picture. So this is your current value, the guessed value of theta. Now the E step and this red curve here is the actual data log likelihood with the original parameters that you don't know. Now what the E step has ensured is that you get a lower bound using the Q function that we had. So that lower bound is L. So this is the lower bound, right, and which is exactly the expectation that we are trying to maximize. So you use this L function and you get and you know that this is a lower bound, which means it is always lesser than the red curve, right. The important point is that at the E step this bound is tight, which means this is touching the red curve, right, and if you maximize this you will get a new set of parameters which will increase the L value, right. But because this is touching it and because this is a lower bound, it will also increase the likelihood value for the with respect to the original theta, right. So it's a trick because we cannot compute this likelihood, but we know the lower bound, we have computed the lower bound and we are maximizing this, but it is guaranteed to be the new values are guaranteed to increase the likelihood in the original likelihood also, because at this point the approximation is tight and we are maximizing it. Okay. So now again at the next step the E step will ensure that the lower bound that you calculate, the green curve, will be tight, and once again you maximize it, you will get a value somewhere here or anywhere here, and then the next value of theta is again going to increase the likelihood, because every time you are at each step the E step will ensure that you get a proper lower bound and you always get to the you always make sure that it is tight because of the choice of the distribution of Q that we take at each step.
Why would it get stuck in a local optima then? It looks optimum here.
Sorry?
Why will the expectation will reach only after a local?
Yeah, because what if we get at a saddle point? The likelihood curve need not always be like this, right? Right. So for example, the likelihood value can be something like this.
So why wouldn't that curve reach there then?
Well, you can suppose it goes like this, then how it's at this point it is not guaranteed to go up that way. It will just be here in this region. So the usual problem with optimization. So we can say, now we can do this formally. We at the m plus first round we have some parameters, that's the log likelihood of those parameters, and we know that the Q function is a lower bound. We proved it for any Q, any choice of the distribution, the small q, and then this Q value was chosen by the previous iteration's m step. So this equality follows. This is the maximum value of Q which maximizes the maximum over all parameters curly theta, and then this by definition is greater than any Q here, and because this E step bound is tight, we get that this is equal to the logarithm equal to the likelihood in the previous step, which is just the likelihood of the previous step. Okay. So any questions? No? Is this clear? Why it's increasing the likelihood at each point, at each iteration? All right. So now, so that covers the basics of EM. Now let's look at some strange cases. Sometimes what happens is when you are running EM, you tend to get very strange solutions, and this could be one of the reasons. So I am going to motivate this mathematically. So suppose you take your log likelihood for the that you want to maximize, and you set, now suppose you have two components, okay. Well, it does not matter. So take one of the components and set mu1, the mean, to be equal to x1, one of the data points, and set sigma 1 to be equal to some diagonal matrix of dimensionality p, and take some pi 1. So this can be just split into two parts. We are looking at just one Gaussian here, and when you plug in these values, you essentially get this expression, right. Now what happens if sigma 1 square, the variance, tends to 0? This likelihood essentially tends to infinity, I mean this total likelihood, because this value goes to infinity, right. So this is a problem in general with maximum likelihood solutions. The likelihood will tend to infinity, although the fit is really bad. So then this looks like, so the pictorial representation is something like this. What you are doing is you are taking two Gaussians and you are fitting just one data point on one with one Gaussian, and the other Gaussian is fitting the rest of the data points, right. So this is, in most real life cases, this is not a good thing to do, because yeah, it is very unlikely that the data has been generated by two Gaussians like this, one data point from one Gaussian and the rest from the other Gaussian, right. So when you try to do this with just a single Gaussian, do you think you will get this problem? Why? Yeah, but suppose you have, suppose I give you, take unidimensional case, and I fit this one Gaussian here. This, it is, there will be a non-zero probability of a point coming from somewhere here, right, even if this is the mean. So intuitively we would think that the blue Gaussian is what might have generated this data with so much variance, right. But there is a non-zero probability that the data has been generated from such a Gaussian. So why will we not have this problem there?
It is not a locus optimum.
Yeah. So the maximum likelihood solution will never give you this. Maximum likelihood solution is most likely to give you something like this, right. When you work out the likelihood, the likelihood for this, the pink Gaussian, is definitely going to be lesser than the likelihood for this, right. And again, this is just due to the mathematical form of the Gaussian mixture. So this, because of the summation, this is really happening, because it is possible that you can fit the data like that in a way that the likelihood goes to infinity. So how do you deal with this? The simplest way in a frequentist framework is to just keep, when you are running EM, you check whether it is happening or not, and if it is happening, then you just reinitialize the parameters. So you keep trying to detect such collapsing components and try to do it. And in general, actually it is better to restart EM several times, because EM is so as you know, it can get stuck at a fixed point or a saddle point. So, with different initialization parameters you can get much better solutions, as we saw in the simulation as well. Right. The Bayesian solution is to take priors, right. You take priors on each of the parameters, and it turns out you can work out the math and see that the expectation, the E step remains the same, and the only difference necessary is the additional term in the M step that we need to maximize, and this usually solves the problem by choosing right priors. Right. So, now let us come to finding k. Till now we have assumed that we know the number of components, and how do we find k? There is no really good solution to finding k, and what statisticians usually prefer and what works well in practice is to generate many candidate models. You look at the data and you assume that okay, there can't be lesser than 3 components here, there can't be more than 12 components here. So, let us run EM for all these different values of k, and you choose that k which minimizes some criterion, okay. And there are different criteria that people have discussed. For example, it is something like the regularization that you do in other models. You basically penalize high values of k. So, the AIC Akai k information criterion is this. It is just the log likelihood plus k. So, minimizing this will give you the least number of components which can explain the data well. Right. There is a Bayesian information criterion which uses k log n, similar general idea. And then there are other approaches for finding k which are Bayesian non-parametric approaches, where you assume some Dirichlet process priors, and then the method itself automatically estimates k. Right. Right. So, the algorithm that we discussed in that form was given in 1977. So, you can imagine that a lot of work has been done on EM since 1977. There are a lot of different kinds of EM algorithms. There are online versions that work on large streaming data sets. Like I said, EM is designed to find local maximum. So, there are annealed versions that increases the chances of finding global maxima. The simplest solution is random restarts, but annealing does something more. Variation. So, sometimes, so in the case of Gaussian, we saw that the E step and the M steps, they were computationally tractable. We could derive analytical formulas for these. But in a lot of cases, if there is time I can show you one, we will see that they are not computationally tractable, and sometimes you need to do additional things. So, there are variational versions of EM, there are stochastic versions of EM, Monte Carlo versions where you have intractable E steps. There is something called generalized EM, which was one of the earliest algorithms where you have computationally intractable M steps. Then when you have sequential parameters, dependent parameters, then there are other versions of EM, and in general EM is quite slow, right. So, your each step within EM within the iteration is computationally not very expensive, but convergence is usually very slow, and it is especially slow when you have lots of missing data or lots of latent variables to infer, right. So, there are many many approaches to deal with it. There are these Aitken acceleration techniques, over relaxed EM, and so on. So, to summarize, like what I said, the major advantage of EM is that it monotonically increases the likelihood. It guarantees that if you take any distribution, any mixture model, or anything, any likelihood computation where there are hidden variables or latent variables, and you apply EM, and if you follow the formulas carefully, you will guarantee that the likelihood is increased except at fixed points, and it is usually numerically very stable compared to other techniques like gradient descent. It is easily implemented, and the interesting thing is that many problems can be modeled as incomplete data problems. We saw that in the case of Gaussian mixture, there was no missing data in the beginning, but we assumed the latent variables to be missing. The disadvantages, as I mentioned, is slow convergence, and there are no guarantees of finding global maximum, and the steps may be analytically intractable. Yeah. So the two standard references have very nice explanation for EM, and there are very nice tutorials also available. Matrix cookbook you should be familiar with to get all your matrix derivatives, and this is the standard reference if you want to go really deep into EM. McLachlan and Krishnan's book on EM, the whole book is on EM algorithm. EM can always solve it, but it may not be able to solve well. That's the, if there are lots of missing data, then usually the it doesn't give good. Right. So there is some there is a lot of work on so these estimates that you are getting. You may sometimes want to know how good those estimates are, right. So you want to get the standard errors on those estimates. So there is so in fact that is one of the flaws of EM, it does not automatically give you that, but there are methods to deal with that. For example, there are some bootstrap methods that can give you estimates of the error, that you error estimates for the estimated parameters.
In that finding K, you had K max and K min, right? How do you get those two parameters?
Yeah, they are also guessed. So that's something you have to guess based on the data that you have. So if you take the standard R packages like mclust or something like that, they usually have some default parameters 2 and 12 or something like that, but then you can set them. So when mclust runs and gives you like what I showed you in the simulation, when it runs and tries to find the parameters, it runs it for all those different values of K and takes the best one with respect to the likelihood. Okay. So it will be a good exercise, I think, like if you take some different distribution, so take something like Bernoulli, some very simple distribution, and work out the math, it will be quite nice to see how it works out. And yeah, even the other thing that I didn't work out here, this part is also quite simple to do. Assume that there is a prior and see how it works out. But the general idea is clear, right? Okay.